This lesson is for section 8.5. Today we're going to be graphing our tangent function, and then we're going to take a look at all of our reciprocal functions as well and graph our mother functions. So that's really our main objective for today, to make sure that we understand what the behavior of each of these functions looks like, and then to be able to graph them on a period that we're going to use from 0 to 2 pi. We are also going to graph transformations of these functions. So we're kind of putting a lot of stuff all together into one section here because we are going to have some phase shifts and our periods will change as well. But because you've had some background with that already, I'm hoping that this will be a pretty easy transition for this lesson. Okay, so let's start off actually by filling out this table. Before we get into graphing the tangent function, I want you to look at this table and fill these out. So this is just going to practice some of your trig values. Now when you fill out the tangent of x, remember that tangent of x is really the ratio of sine to cosine. So once you have your values filled in across for sine and cosine, you're going to simply divide the sine divided by cosine here. Okay, so please go ahead, pause the video, and fill those out. Okay, so here's your table all filled in. Now, I hope that that was easy peasy lemon squeezy for you. Those trig values should pretty much be second nature to you at this point. You should probably be able to fill out that table in under 2 minutes, I would say. So I hope that by now you're making the transition from like rote memorization to thinking about where pi over 6 is. Remember, the pi over 6 families are closest to the x-axis, which would mean they have the largest x value here in that segment here is the largest, and the sine is the smallest. So that's how you can quickly find those values. Okay, anyhow, I want to take a look now at our tangent function, and I want to see visually how it relates back to our unit circle. So what I'm going to do is create a radius here. Now we know our radius here has a radius of 1 in our unit circle, and if we were calculating the tangent of this point here on our unit circle, we would be looking at the ratio of sine to cosine. Now because our sine to cosine ratio, because the sine here is 0 and our cosine here is 1, it would be 0. Now what we're looking at is really the change in the y value over the change in the x as we continue to move this radius through our unit circle. So for example, if I were to now redraw that, and it's hard to show the motion, but imagine that now that radius has moved to this position here, okay? And let's just say that that corresponds to an arc length of pi over 6. Okay, so we have pi over 6 radians, which corresponds to an arc length of pi over 6. Now, let me erase this real quick. Now we have a larger y output here. Okay, this y value here is larger. This segment, the x value, has shrunk a bit as we wrap and rotate that radius around our unit circle. So as we continue to get closer to this point here, the y value obviously increases, right? So here's another segment drawn in, the radius drawn in again, and that cosine here value decreases. But really what we're looking at, again, is a change in y over change in x, right? Which I hope you recognize that as slope. So tangent is really the slope of that radius. Okay, so the tangent is the slope of the radius, which is connecting the ratio of the sine to cosine. So it's the change in the y over the change in the x. Now let's talk about what the radius and the slope is of that radius. Whenever you are in, let me erase all that. Whenever you're in the first quadrant here, so from 0 to pi over 2. So look, from 0 to pi over 2, this radius has a positive slope. So you're going to notice that all of these values here are positive. Now as we get closer to pi over 2, these values increase. So we're seeing an increase here in our values for tangent, but as soon as we get to pi over 2, now our slope, we've learned this way back in Algebra 1, this is an undefined slope. Okay, the slope of a vertical line is undefined, which is why we have a value here that is also undefined. Now as our radius travels into the second quadrant here, notice that the slope of this line here becomes negative. So as soon as we move past this pi over 2 mark here and we move into the second quadrant, now all of a sudden we have a negative slope. Okay, that negative slope becomes less and less steep, right? So here the slope is less steep and even less steeper. I don't know if that's a word, but it gets less steep as we move through that second quadrant, which is why we see our values here. They're negative, okay? But they get smaller and smaller until they finally get back to 0 once we get back to pi, okay? So we're seeing of the slope here of a horizontal line, which is in fact 0, which corresponds to this value here at pi. Now as we move into the third quadrant, so again we're rotating that radius here and we're moving it into the third quadrant. Now we have a positive slope. Okay, so we have a positive slope here. And as we move away from pi and closer to 3/2 pi here, that slope gets steeper and steeper and steeper until we get to, again, an undefined. So we're seeing it grow, the values grow larger, they're positive, and they come to 3/2 pi and become undefined again. Well, that's right back to where we are here. Okay, if we see our values here, they start at 0, they get steeper and steeper until we get to undefined. Okay, the reason why it's undefined is as you have a larger axis here, I'm sorry, not a larger axis, but your y value is larger, you're taking your sine here, which is getting closer to 1, right? Closer to 1. And the value of your cosine is getting even smaller. So we get 1 divided by something very small, which is why it becomes undefined, okay? Because it's just huge. The smaller this number is, the more it fits into 1, okay? So it becomes larger and larger and larger. Okay, now finally, as we mark our way or move our way through the fourth quadrant here, that radius switches back to a negative slope. You can actually visually see that this slope here is negative, okay? And again, we're going to be seeing then these table values repeated. So, more like these. So we have a steep slope here. That's a pretty steep negative slope. But as we move closer to back to 0 or 2 pi, okay, we see that slope kind of flattening out a bit, okay, until finally it gets back to 0. Okay, so I think we're just about ready now to graph our tangent function. What I've done now is cleaned up this diagram just a little bit here to show that when you have your radius in the first quadrant, that radius would have a positive slope. So this is just representing the slope of that radius, which is corresponding to our values for the tangent function. So when we graph this, we are actually going to graph 0 to 2 pi, even though in a lot of textbooks and many teachers also will graph from negative pi to pi over 2, and that's because you do get one full period from those values. But I'm going to keep it consistent with what we've been doing so far with all of our graphs. So I'm going to break this down into, again, our 4 intervals here. So I've got 3/2 pi, pi over 2. Okay, now we know that our tangent function, since the tangent is sine of x over cosine of x, that the tangent function is going to be undefined at values of pi over 2. So at values of pi over 2, or multiples of pi over 2, I should say, that function will have an asymptote because it can never equal any value multiple of pi over 2. So from our studies in graphing with asymptotes, we know that our function will always tend towards those asymptotes. Now, our tangent function, we look at our first value here, we had an input of 0, and our tangent is 0. So we're here, it's our first coordinate. Now you could always, when you're graphing these, plug in values, into your trig functions and try to graph. Is just a very tedious way to do that. So let's talk about, since we have an asymptote here, we have our starting point here at 0, 0. We knew that all the values between 0 and pi over 2, those were positive. They started off small, they got larger and larger and larger until they approached pi over 2, where they're going to just tend towards that asymptote. So our first branch will look like this. Now, the reason why this is going to positive infinity, and I talked a little bit about this before, but if our sine is 1 and our cosine is a very small number, right, as it approaches pi over 2, the sine becomes 1, our cosine becomes smaller and smaller and smaller. This number fits more times into 1, which means this number is just going to explode. So it's tending towards positive infinity. Now, once we get past pi over 2, and we move into the second quadrant, so that's showing the pi over 2 to pi, right? This this value here. Our slope is negative. It starts off very steep, but it's a very steep negative slope. So we're down here on the other side of that asymptote, and we get closer, or well, it flattens out, right? So we get closer and closer and closer here to our x-axis, and at pi, we get the value of 0. We're at 0 here. And then all of a sudden, it repeats those values as we swing into the third quadrant. So from pi to 3/2 pi, we end up with a branch that looks exactly like this. So we've got that going on. I don't know why I switched colors. Let me go back to this. Okay, so it's going to go through, and again, that value gets larger and larger and larger and larger, and then tends towards positive infinity as it approaches 3/2 pi. And then from the other side, it becomes negative again once we get back into the fourth quadrant here. So as we swing through the fourth quadrant, that radius has a very negative steep slope. So we're here, and it will widen out, right, and get closer and closer to the x-axis, where finally at 2 pi it becomes 0, so the slope is 0. So this is your basic tangent graph. Okay, now there are some special coordinates also that we could graph on this tangent graph, and that's the value pi over 4. So sometimes you'll see values like this, pi over 4, 3/4 pi, and that's because we know what the tangent of those values are. That's 1 and -1, right? And we know that because 1, we could graph it here, but oops. Pi over 4, the tangent is 1. At 3/4 pi, we have a tangent of -1. So that really is only going to come into effect when we start to transform the tangent graph. So if I had 2 times the tangent of x, it really doesn't affect your amplitude per se, because this value here is going to go to positive infinity no matter what. So you can't really say that you have an amplitude. That's why over here I'm just going to fill in that this is undefined. We can't define this amplitude. It just goes to positive or negative infinity. But what we can do is indicate if this was 2 times the tangent of x, then these values here on the side on our y-axis would be at -2 and 2. So I'm not going to get that picky with you, but in your textbook I know there are a few problems like this, and that's the effect of these values here in front of your tangent and your cotangent graphs. And we'll talk about cotangent in just a second, but this is, let me erase here, this is your most general graph for the tangent graph. Okay, so let's talk about its period. Well, you got to be careful here, because even though we're graphing from 0 to 2 pi, that does not mean the graph it has a period of 2 pi. It actually only has a period of pi, because you can see one full interval here between pi over 2 and 3/2 pi, so the period is only pi. Now the domain is all reals except where we have our increments of pi over 2, or our multiples of pi over 2. So except pi over 2 multiples, so positive or negative pi over 2, positive or negative 3/2 pi, and so on. Okay, our range is all reals, so from negative infinity to positive infinity. So again, this is the basic graph for your tangent function. Alright, when we graph the cotangent function next, we need to remember that cotangent is really the reciprocal of our tangent function, which means it's cosine over sine. Now that also means that wherever our tangent function was 0, then our cotangent function will become undefined. Now if we look back up at our sketch here, our tangent function is 0 at all increments of pi, so at multiples of pi. So at positive or negative pi, our tangent is 0. At positive or negative 2 pi, our tangent will be 0. So that's one of the things too that defines a tangent graph, is that you're always going to have x-intercepts at multiples of pi. But anyhow, that's going to create a vertical asymptote in our cotangent graph at those values of positive or negative pi. So at increments of pi here, let's draw on our axis, and again we're going to go 0 to 2 pi. We're going to have vertical asymptotes here, because again our tangent function is 0 at these values, which is going to create a vertical asymptote in our cotangent function. Now we also have a vertical asymptote actually at 0 here, so our y-axis is a vertical asymptote as well. But now when we look at our values here, for cosine over sine, wherever cosine is equal to 0, our function is going to be 0. So that happens at pi over 2 and 3/2 pi. Whoa. So we have x-intercepts here at pi over 2 and 3/2 pi. Now we can graph the rest of this function based off of just how the graph behaves when we have vertical asymptotes. From 0 to pi over 2, we know that our function has to be positive. This ratio of cosine to sine must be positive. So we're going to have to hug this vertical asymptote here above the x-axis, and then it's going to get closer to 0. So as our values of x increase, we get smaller and smaller values until finally we get to 0. And then when we go into the second quadrant from pi over 2 to pi, that ratio becomes negative, right? Because the cosine becomes negative. So in the second quadrant, we have a negative cosine and still a positive sine. So we're going to flip across the x-axis here into the negative part of our graph here. And we're going to have values that, again, they start off, small, but then they get very, very large in the negative direction, so they get more and more negative. And again, if we go through our circle, unit circle, back into the third quadrant from pi to 3/2 pi, these values become positive because both the cosine and the sine are both negative here, right, in the third quadrant. So we are back up here. Our graph hugs that asymptote. It gets closer and closer to 0 as x increases, then flips once we get into the fourth quadrant, because now our sine is negative and tends again towards negative infinity. So this is the graph here of our cotangent function. In fact, it actually looks just like our tangent function, just flipped over the x-axis and shifted over pi over 2 units. So let's talk about its amplitude. Just like the tangent function, it's undefined. Its period is similar because here we have a full interval from 0 to pi. So our period here is just pi, just like tangent. The domain is all reals except multiples of actually pi this time. So 0, positive or negative pi, positive or negative 2 pi, and so on. The range is all reals, so from negative infinity to positive infinity. Okay, so while I was just graphing number 1 here, my dog just farted, and I swear it was my dog and it wasn't me. And so I'm re-recording this part, which makes me really mad because I did it all in one take. So yeah, that was really gross. Anyhow, okay, so we're graphing our first transformation here of the cotangent function. Now we're going to use the same strategy that we've used before where we trap this between 0 and 2 pi. So we're going to solve here for x. Dividing out the pi, we end up with an inequality 0 is less than or equal to x, which is less than or equal to just 2. So I take my axis here. I have 0 to 2. I'm going to cut that up into my quarters here. Whoa, it's 3/2. And 1/2. Okay, now we have vertical asymptotes at 0, at 1, and at x equals 2. And because this graph, this cotangent here, has that negative in front of it, that means it's going to flip over the x-axis. So instead of looking like this, our graph now looks much more like the cotangent function actually, where it's got we've got intercepts at 1/2. It's going to come through like this, intercept again at 3/2, and through like that. Okay, so there's our cotangent graph. Now the 1/2 out in front, remember how we talked about this with the tangent graph. This is something that you're going to see in your homework, so I might as well just show you it now. At 1/4 here, we would have the value of negative 1/2, and here at 3/2, or I'm sorry, 3/4, we would end up with a value of positive 1/2. So it just shrinks that graph here by a factor of 1/2. Okay, so let's talk about the period. The period here is 0 to 1. So 1 is my period. And again, you could just take this and divide that by 2 to find the period, because we have to cut that in half, and it's not just the difference here. Our phase shift is 0 since it didn't move from the x-axis, so I'm just going to say none for this. Okay? Okay, our next reciprocal function is the cosecant function. Remember, cosecant is the reciprocal of sine. So cosecant is 1 over the sine of x. I've got the graph of a sine function here because we're going to graph just right on top of this. It's going to help us determine what the cosecant graph looks like. So let's think about what happens when the sine of x is 0. If the sine is 0, then we end up with an undefined value for our cosecant graph. So anywhere we see an x-intercept on our sine function, we actually have a vertical asymptote for our cosecant function. So we've got vertical asymptotes here. And although we do take the reciprocal, there are some values that are going to be the same on our cosecant graph that are shared with our sine graph. And that's going to correct a value like pi over 2. So the sine of pi over 2 is 1, and if we take the reciprocal of 1, we still get 1. So our first coordinate here that I'm going to graph on our cosecant function is shared with our sine graph. Now if we take the reciprocal of negative 1, which occurs at 3/2 pi, we end up with negative 1 also, so these values are shared, and over here I just repeat myself. So these are points on our cosecant graph. Okay. Now between 0 and pi over 2, though, something very different happens. Let's say we look at the sine of pi over 6. So sine of pi over 6 is 1/2, about right there. If we take 1 over 1/2, this number becomes 2. So that jumps up here, about right there. I guess that might be where 2 is on the graph. And it's going to happen again over on this side. So we have that point here now on our cosecant graph. Now if I looked at a value, like a very small value of our sine graph, so let's say our sine output is very, very tiny, and I take the reciprocal of that very tiny number, well, I end up with a very large number, right? We talked about that because it fits a lot more times into that 1. So we actually tend towards our asymptotes here, and that's y. But this is what our general shape will look like. Now when we go to pi to 2 pi here, our function is negative. Same thing happens, you just have a very large negative value, so it gets more negative. And then it repeats back over here after 2 pi. Okay, so these are what the branches of our cosecant graph look like. So they're not parabolas, don't think of them as parabolas, they're not quadratics at all, but they do look U-shaped. So let's just graph it one more time. Our general cosecant graph, we're going to graph from 0 to 2 pi. We have asymptotes at pi, 2 pi, and 0, because that's where our sine function is 0, making our cosecant undefined. Okay, we have values, pi over 2 is going to equal 1, so let's just show that here on the side, and 3/2 pi will be at negative 1, and it tends towards its asymptotes, like so. Okay, so this is our graph of our cosecant function. This is the general mother function shape. Now its amplitude, we don't have one. It's again undefined, so there's no amplitude. You can write either none or undefined here because it goes to negative and positive infinity. The domain here is all reals except multiples of pi. I always forget to write 0, but 0, positive or negative pi, positive or negative 2 pi, etc. Our period is 2 pi, so it would take 2 pi for that to repeat itself again over here. Okay. Our range, this is a little bit funky of a range because we go from negative infinity all the way up to negative 1. So negative infinity to negative 1. We're going to put a parenthesis and then a bracket here on negative 1 because negative 1 is included here. And it's joined by another range here from 1 to positive infinity. So bracket 1 to positive infinity. So that's the graph of your cosecant function. Okay, next up we have our secant function, which is the reciprocal of cosine. So secant is 1 over cosine. So that means that whenever cosine is equal to 0, our secant function would be undefined. So we end up with vertical asymptotes here at all of our multiples of pi over 2. So I'm going to just draw that in, and it's really easy to see where, cosine is equal to 0 from the graph here of our cosine function. So we're just going to overlay again right on top of our cosine function. Now similarly, whenever the cosine is equal to 1, which happens at 0, 1, pi, it's at negative 1, but at 2 pi, again back at 1, those points would be shared on the graph of the secant function because we're just taking the reciprocal. Now from 0 to pi over 2, our cosine will always be positive, and our secant function then would always be positive as well, so it's going to tend towards that vertical asymptote. So for the same reasons that we talked about, when you take the reciprocal of these numbers, a very small number will become very big. This is why it's going to tend towards positive infinity. Now a negative number, even at a value where the cosine here is very tiny, it's a very tiny negative number, then it's going to become a very large negative number. So it gets more negative. Okay, so this is the graph and the general shape here that we're going to see, and it's going to repeat here. Okay, so what we're going to do is graph from 0 to 2 pi. So, of course, this is going to look like that on this side, and then here we would have another shape. Again, these are not parabolas, they're just U-shaped. So let's graph this mother function here from 0 to 2 pi, and we'll fill out the above information. So let's see. Where we have multiple of pi over 2, so this 3/2 pi and pi over 2 here, we're going to have a vertical asymptote. And our cosine graph starts at 0, 1, and our secant graph also has the coordinate 0, 1. It's going to tend towards positive infinity, and then when we switch into our second and third quadrant here, the cosine is negative, which means that our secant will also be negative. So we have, oops, let's put a 1 there and a negative 1 here. Here's another important point. At pi, cosine is negative 1, so our secant is negative 1 when we take the reciprocal. And we're going to tend towards negative infinity here. Once we switch to our fourth quadrant from 3/2 pi to 2 pi, our value for cosine is again positive. And it's going to be a very large value and then gets smaller and smaller until it hits 1, and then it's going to go back up this way. So what we're going to do is just show these values here. This is the shape that I want to see. So it's really one full period here, because if I went and drew that in, you'd see this branch here repeated. So this is what we're going to show for our mother function from 0 to 2 pi for our secant function. So let's fill this out here. The amplitude, again, is undefined. There is no amplitude. The domain is going to be all reals except increments of pi over 2, so multiples of pi over 2. And our period is 2 pi. So we have a period of 2 pi. The range here, similar to our cosecant function, it is going to be from negative infinity to negative 1. And, oops, there should be a bracket here around the negative 1. And from 1 to positive infinity. Okay, it's worth mentioning, too, that this function here is an even function. Just like the cosine function was even, our secant function is an even function, and then up here the graph of sine is an odd function, and here you'd see it as an odd function as well because it is symmetric about the origin, right? So you can see it's symmetric about the origin, while here this is clearly symmetric about the y-axis. Okay, so we're almost done, and we're actually going to do these pretty quickly. So let's trap 2 pi x minus pi over 4 between 0 and 2 pi, and we'll solve for x. So we'll add pi over 4. Okay, and now we'll divide by 2 pi. So what did I get here? 9/8. Okay, so let's draw in our axis here. We've got 9/8, 1/8, and we'll cut that in half and then into quarters. Okay, so we get 5/8, and then 3/8, 7/8. Okay, so one of the things I actually think would be really easy for you to do is just to sketch in the cosine graph, because we know that this is the reciprocal cosine, and it's just going to help us determine where the values are for our secant graph. So if this was -3 times the cosine here, I'd have an amplitude of 3, so 3 and -3 here would be the key points, and I would start with my cosine graph up here, but since it's negative, it would be down here, right? It's going to be flipped over the x-axis, and then I'm just going to show what that would look like with my cosine function. All right, so that's going to help dictate how I draw in then my secant function. So remember, anywhere the cosine is equal to 0, you get a vertical asymptote. So you can just draw in the vertical asymptote right over this. And that's 7/8 as well. And then here we have this coordinate defines the graph, or the secant point as well. So we can just tend towards our asymptote here. We're going to create another U up here. And repeat that down here. So then after that I would just erase. It's harder to erase here on the computer, but whoa, I just got rid of a bunch of values. But on your paper, obviously, it'd be much easier to erase that. So that would be the graph here of our secant function. All right. Now the period here is just going to be 9/8 minus 1/8, so 1. Our phase shift shifted over 1/8 because it usually started at 0, but it shifted over 1/8. All right, this next one here, let's again set x over 4 plus 5, 6 pi between 0 and 2 pi. And I'm just going to pause and solve for x. Okay, so we'll begin by drawing in our axis here. 14/3 pi, negative 10/3 pi, and then we'll find our 4/4 here. Okay, so halfway between negative 10 and 14, that's going to give us 2/3 pi. And then we'll find the difference between negative 12, so negative 4/3 pi, and over here, if I add 6, 8/3 pi. Alright, so there's my x-axis. Again, I want to draw in the, in this case, the sine function here, and it's not flipped or anything, so I'm just going to lightly draw in a sine function through here. And if it had this 4 here, to adjust my amplitude, so this value here, let's just draw on a y-axis somewhere in here. Oops. Okay, so this would be 4, negative 4. Okay, now at this point I can draw in my vertical asymptotes here because I know that one is going to exist. Let's do this in, let's do blue. Wherever sine is equal to 0, my cosecant function is undefined, so I'm going to draw in a vertical asymptote here. Vertical asymptote at 14/3 and a vertical asymptote at negative 10/3. And then I just look at the point that they're going to share and draw in now those U shapes. So down here, oops, it's over here. There we go. It's not really at negative 4 here. There's negative 4. Let's adjust that. And there you have it. So that's the graph here. If I erase this, I'm going to erase more stuff than I want to, but whoops. There's the graph of 4 times the cosecant of this guy. Okay, so let's talk about the period. The period here would be 24/3 pi. So 24/3 pi, because that's the difference between these two values here, so 8 pi. The phase shift here is negative 10/3 pi because we were using 0 to 2 pi and we shifted it left to 10/3, or negative 10/3 pi. Alright, that's the end of the lesson. I know it was a long one. Thanks for sticking in there, and make sure you get a lot of practice with this tomorrow in class.